our next lab introduces you to a tool that you're going to be using a lot of as you develop code. It's one of the most powerful tools that, that's available. It's called GDB. So GDB is the GNU debugger, which is its own wonderful thing. I don't know if you guys are, so GNU is a kind of yak. It's a ram, I guess, that I think lives in somewhere in Asia, I guess is where it's most commonly seen. And it's actually an acronym. It stands for GNU's New Unix, where it continues to recurse. So the GNU and the GNU's New Unix also means GNU's New Unix. So it's a really long name to write out all the way, which is why people just abbreviate it. Okay, so anytime that you see GDB or any of the other G tools like G++, that's also sort of encoding that regression joke, I guess, that computer scientists love to make. Okay, so GDB is the GNU's debugger. It's a powerful tool for examining programs while they're running. What you're allowed to do is stop the execution of the program in the middle of it. And while it's running, while it's in some particular state, you can poke around and look at the variables and see how you arrived at a function, what function's called the function you're looking at, and what are the states of the variables that you're on. So I don't know if, I think a number of you saw errors, maybe not all of you, but relating to index out of bounds, like an assertion error that gets made by, say, utility vector 1, right? And those assertion errors aren't, they're not great on their own because they don't tell you where your bug is. They just say, hey, look, you got a bug, right? So the GDB debugger allows you to stop execution at the time that you stepped out of bounds and then figure out where in your code you stepped out of bounds and what are the variables that led you to go out of bounds. So it's probably some index I. It's equal to 20 and your array size is 19. And you walked off the end of the array. But why did you even get to 20 in the first place? And you can look at the other variables that are surrounding I. And you can be like, oh, I added 10 and 10 here when I meant to do something very different, right? And that's why I ended up with an I value of 20. And you can find your error. So there are 4 different ways to stop execution. You can set breakpoints. You can say, I want to run until I get to this point in the program, and then I want to stop. So you would label the file that you want to stop at and the line number. You can have assertion statements, like assert that the index I is greater than 0, or that it's less than or equal to the size of this array. So that's what the utility vector 1 does. You can have it stop at, when exceptions are thrown, and you can have it stop when, if it's running and you don't know why it's taking so long, you can stop it by hitting Control-C. That's really useful if you write a loop that doesn't terminate, so that you can figure out why your loop just keeps going and going and going and going. The alternative methods are usually to have something get printed out. And that's great for maybe the first 10 iterations through this infinite loop. But once you've been in this loop for 10,000 iterations, your scrollback buffer is so long that you no longer have any idea of what was happening just before it started printing out this useless error message. Okay, so I'm just going to tell you about a couple of functions, and then there's a lab that's associated with it. I've given you a program that doesn't work, and I want you to figure out why. All right, so here are some functions. You can say, run my program, and in this example, I'm giving you a unit test suite. You'll compile the test suite. The name of the test suite is GDB exercises test, or exercise test, singular. And it's going to be compiled as part of the protocols .test executable. So when you open up GDB, you'll open it up with the protocols.test executable, and then you'll run it as if you want just a single unit test suite to run. So this is on this you would give all of the arguments to your executable. So if you wanted to, you could have something like dash database equals path to Rosetta main database. Okay, so all right. If you want to look at a variable, let's say you've got this variable x and it's giving you a headache, you can look at it by printing out its value. So you say print x, you give the variable name. X has to be in the scope that you're looking at, right? So if you pause the program and it's in the middle of some function and you want to look at some value up in main, you have to get to main before you can print x. If you have, and I'll tell you how to do that in just a moment. If you have a class and you want to look at data members of that class, then you can just use the dot operator. You can get into the class. So this is your class instance foo, and you can look at its data member bar, and that will print this out. It doesn't matter if bar is private. You don't have to invoke only public functions of the classes. GDB lets you peer into the private lives of your classes. Okay, so I just told you that you need to be in the right place in order to look at a variable. So if you want to see x, you have to be in the function where x lives. So let's just talk about the stack for a moment. So you can get a backtrace. You can figure out how you got to the particular function where you got paused, and it will give you back information about the functions that are on the stack. So the function here is going to be these are all the functions that are on the stack. So where you are currently is 0, 1, 2, and 3 is say one that I'm highlighting. So this is the place on the stack. This is the fourth function up from the bottom. This is the location of memory. That's not very interesting. It will tell you the name of the function. In this case, it's __gi ___ assert fail. And then it gives you the arguments to the function. So that's this to, wow, it's a long one. Supersize. I feel like I'm missing the end here. Static type, less than supersize, comma, 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 comma. And the standard operator reference is also an argument to this function. And that's the end of that. So these are the arguments to this particular function. It will tell you the file that this function lives in and the line that function is within that file. And then as you go further up the stack, yeah, I think I was just telling you about the argument list. So this is the argument to this function operator. It was given a very large value for I. And so this is an assertion failure from a utility vector 1 where I indexed out of bounds. I didn't allocate an array that had space for this many elements. This is an error you're going to see. Like explicitly, this is one of the errors that's in the exercise. Okay, so how do you get to the error? Like, how do you get to where I got to that crazy value of 18 quadrillion? Well, you have to be able to navigate the stack, and you do that by using up and down. So up will take you from the bottom of the stack, which is now at the top of the screen, and it will bring you from 0 to 1. So it will take you from this Linux raise.cc to abort.c, right? So you can keep running up to get to your function where you actually had that crazy value of I. So, right, just one thing that's weird is the stack grows downwards, right? So you start at main, and then you call some function of main like test exercise or something like that. And then you call some other function like operator bracket, which is where I'm trying to get into this utility vector. And then that asserts a boundary condition, so I'm growing downwards, and so somewhere in the boundary condition, I triggered an assertion failure, and that brought me through like 18 functions, and so I'm down here at the bottom, and I need to get back up to maybe not main, but the test that's being run. So we're going upwards. The confusing part of this is that the topmost function is the one that you're going to be doing. So you're actually descending when you say up. It's great. Okay, so so if you've gone too far up, then you can go backwards by using down. Break lets you say to GDB, I want you to stop at a particular place in a particular file. So you would give the line number and the file name. And so in this GDB exercise test, you might want to stop at line 34. If you were to do so, and then you were to run the program, let's say, so this is shorthand. I ran the program once, and it crashed. And then I stopped, and I said, OK, let me put a breakpoint in this file at this line, and let's run it again. And I can do it with just the letter R. That will give it all of the command line arguments that it used the last time that it ran the function. So you don't have to retype out all the command line arguments. So it saves you some typing. Yeah, Amanda?
So I was supposed to say add a breakpoint on line 34?
Do I have a typo? Yes. Colon 41. I found that line 41 wasn't interesting, and so I went back and made it line 34. Okay, so that's how you would add a breakpoint on line 34. There's no like offset by 13 or some crazy thing like that. It's just a typo. Yeah. So if you have a breakpoint and it's you don't want it anymore, you can delete it. You delete it by its index. So this was the first breakpoint that I added. And so I set breakpoint 1. This is also a typo. That belongs down here. The breakpoint message comes after I type break. And so I ran run again. And let's say it was in the middle of an infinite, or not in the middle of an infinite loop, but some loop that runs many times that I'm not interested in breaking in every time I go through it. Let's say it goes through 10,000 times, and it's running just fine. Then I can delete that breakpoint, and it won't stop me there anymore. You can disable a breakpoint if you think you might need it again in the future, and if you've disabled it, then you can re-enable it with the enable function. Yeah, Amanda?
So we would delete one where it says breakpoint 1 binomial coefficients 7 plus 1. So it says delete 1. What are we?
Yeah, so the 1 is in reference to which breakpoint I've added.
So that's in your code?
No, it's in my GDB session. So in this session, I've got exactly one breakpoint that I just added right here. So that's breakpoint 1. And so when I want to disable this breakpoint on this line, then I refer to it by its integer, its index. So if I added another breakpoint, then that would be breakpoint 2. And if I wanted to disable breakpoint 2, then I would do disable 2. Yeah. Next, executes the code on the current line that you're stopped at. And so you can go up and down the stack and find a particular frame that you're curious about, and then you'll be on a particular line in that frame, in that particular section of the stack, and then you can just execute the code that's on that line and go to the next line within that frame. So if you're very far down in the stack, you can, you're some low-level function, like you're just returning the XYZ coordinate of an atom. You can go to the next line where that function exits or something, and then returns to the calling function. Or if you're way up where you're initializing a pose from a PDB, you go to the next line, you'll just finish initializing it from the PDB, and then again you'll be stopped, but once that pose has been initialized. So in this case, in my example here, I'd set a breakpoint on line 34, and that was at this line where I'm initializing this vector of size n, and I want that to just happen. So I want to step sort of to the next execution, so I say next, and that brings me to the next line in this file. This is line 35. So it tells me what line I'm on, and the contents of that line. said next, and I'm on line 35 now, and this is the contents of that line. This line hasn't yet executed, and execution has stopped. So I'm waiting, GDB is waiting for user input. If you're really interested in how a function actually executes, you may step into that function with the step command. You can either type out step or you can just say s. So in this case, I was on line 35, and I want to see how this gets constructed. And so I step into this, and that will take me to this allocator function deep into it. And there's the function. It's on line 37 of, this is provided. This is user include, right? I mean, these are files that the system provides. And so allocator just has like an empty constructor. And that's what it does. Okay, so that would take me into this. I think what's going on here is that I've got a template, and so ordinarily you would step into the constructor of the parameter because of templating and the copy. And so when you have a template parameter, the compiler does a lot of things with the original code, including, I guess, removing a bunch of things like the constructor, which is maybe a little confusing. Okay, so that would take me into this file, and then I could see everything on the stack above it, which should just be the function that I was in on line 35. Okay, so you can, if you've looked at some variables and you've determined that everything's okay and you just want the program to continue execution, then you can use the continue command. It just means, okay, just keep running and go to the next breakpoint or go to the next assertion failure, just run. And then you can stop execution either by first putting a breakpoint in, or when it's run long enough, you can hit Control-C, and you can stop execution again, and GDB will listen for new commands. All right, so there are a couple things that will save keystrokes. If you want to execute a command that you've already executed, you can hit up arrow, and it will take you through your history of commands, just like you can do in Bash. When you're in the shell, you can hit up arrow, and you can get through your history of commands. The last command that you just executed, you can re-execute by just hitting enter. Just hit enter, and it will do the same thing again. That's really convenient if you're stepping through functions, right? So you hit S and enter, and then you step one line, and you're an allocator, and it's going to throw, and then there's nothing else there, and so you just hit enter again, and there's somewhere else that's finally interesting, right? Maybe it took you like 20 times to get through it. The great thing about that is that it doesn't pollute your command history with next operations or step operations. At least in my version of GDB, or the ones that I've used, if you want to step through things over and over again, you hit S, enter, S, enter, S, enter. Then the next time you want to execute something besides S, you have to hit up arrow a ton of times to get past all of your S's. Okay, so you can re-execute a command you just executed by hitting enter again. If you have a variable in a loop, and you're, say, have a breakpoint in that loop, then you can continue through the loop and then come back to your breakpoint. If you want to see that variable through each execution of the loop, each iteration through the loop, then you can display the variable. So instead of having to type out print varname every time you go through the loop and it breaks, you can just say display varname, and then when you hit continue, it'll go until it hits the breakpoint again, and then print out the variable name so you can see what it was. This is great for loop counters, especially if you're doing something funky like incrementing the loop counter by some non-standard amount. You can watch the loop counter increment in its crazy way. Other things, I'll put this here so you know it exists, but you're not, like I wasn't able to contrive an example where I needed a hardware watch point. It probably was a good idea that I didn't do that. But if you have an address in memory that's getting corrupted, but not by your code, but by somebody else's code, and then the error happens like, 10 minutes downstream. So let's say I've got a pose, and it's got some coordinates, and then I realize someone's changing the coordinates of my pose. Somehow, I don't know how, but this is the coordinate, I know the address, it's getting changed. You can ask GDB to tell you every time somebody changes the contents of memory at a particular place. You can say break every time someone's changing this variable. And usually when that happens, it's like an array overrun, where somebody's got an array somewhere in memory, and they, it's maybe 20 integers long, and they ask for the index at position 5 million, and that's in your pose, right? And so they write some value in your pose, and suddenly your pose is going to start behaving differently. But it doesn't happen when they write. It happens the next time you try to use your pose. And so you can't find when this happens unless you're able to somehow stop when the array overrun occurred. Right? And so hardware watchpoints are great for that. I mean, that's why we use utility vector 1s and utility vector 0s to really try to avoid places where people write out of bounds and it goes undetected. Because undetected out of bounds array writes, memory accesses, those are way worse than or the ones that, the ones that write out of bounds and don't crash. Those are way worse than the ones that write out of bounds and do crash. Because if they write out of bounds and they do crash, then you know exactly where they wrote out of bounds. There's a trail that leads backwards to it, right? You can stop at the moment of the crash, and you can figure out what happened, what was going on with that array. When they write out of bounds and they don't crash, it's a mystery, and sometimes it goes years before somebody figures out that it's happening, right? And in the meantime, who knows what you're computing, right? Because you've just got corrupted data. So that's why boundary conditions are important to assert in debug mode, so that when you go out of bounds, you know immediately, as opposed to just letting it continue execution. And that's why we don't use standard vectors, because they don't assert boundary conditions with the bracket operator. Okay, so one other thing, you can add conditions upon your breakpoints. So if you have 2 breakpoints in your function, or in your GDB execution, and you want to add a condition for the second one, that at that point in time, some variable that exists where that breakpoint is equal to 15, then you can add this condition that says, I only want you to break when x equals 15. So if you were in some for loop and x is your counter, you can skip the first 14 executions. So from 1 to 14, just don't break there. I'm fine with what happens there. I just only want you to break when it's 15. Then you can do that. You can add a condition to a breakpoint. Since we work a lot with pointers to things, like we have a base class pointer to, say, a mover, you often want to know what that actually is. What is the derived class that the pointer is pointing at? And you can enable that by having this command set print object on. And so that way, when you have this raw pointer to this, or you have this pointer, not necessarily raw, to this derived class, it will just tell you, oh, that's a Pack Rotamer's mover, as opposed to like making you guess. And then if you want to, sometimes we throw exceptions. If you want to have GDB break when exceptions are thrown, then you use this phrase catch throw. So every time an exception is raised, it will break. Okay, your lab is available online.